In this lesson, we will introduce the center of gravity and the centroid. We're also going to talk a little bit about the center of mass, and we will see how to calculate all of these components for simple and for composite bodies. Before we start talking about centers and centroids, let's review a little bit of what we've covered in previous lessons. We know that the resultant force of a distributed load is found by integrating. And we know that the location of the resultant force is found by taking the moments about a point. We did this example earlier in class. We could find the resultant force of this distributed load by finding the area of that distribution. And we could find this area by finding first the area of the triangular section, which would be its base of 6 feet, times its height of 150 pounds per foot, and multiplying them and dividing them by 2. We could also find the area of this rectangular section by taking its base of 8 feet and multiplying it times its height of 150 pounds per foot. Now, the product of feet and pounds per foot is just pounds, which means that the result will be a force. In order to find the location of that resultant force, we would first find the locations of the individual forces of the two sections. The location of the triangular section was located at 2/3 from the small side of the triangle, or just 4 feet from point A, and the location of the rectangular section was located in the center of that rectangular section, which would be 6 feet plus 4 feet, so 10 feet from point A. Let's keep all of this in mind as we look at centers and centroids. First, let's define the center of gravity as the location of the resultant or total weight of a body. We can define the center of mass as the point at which the distribution of mass is equal in every direction. And we can define the centroid as the point at which the geometric distribution is equal in all directions. Let's start first by looking at the center of gravity, which we usually express with the variable capital G. Let's consider the rod in the figure. The rod has a total weight of W, which acts at the center of gravity G, which is located at a distance of x bar from the y-axis. At this moment, we don't know what that total weight is, and we don't know what that distance x bar is. However, we can take a small section of that rod, an infinitesimally small section with a weight dW that is located at an arbitrary distance x from the y-axis. We know that if we want to find the total weight, we have to add up all of the weights of the infinitesimally small sections of that rod. In other words, we need to integrate in order to find the total weight. We also know that the moment that this total weight causes about the y-axis should be equal to the sum of all of the moments that the individual sections with weight dW cause about the y-axis. So we can set this equation, and we can use this equation to solve for my x bar coordinate. This x bar coordinate points to the location of the center of gravity. Now, we're doing this only in the x direction because we can treat this rod as a one-dimensional object. However, if we were looking at 2- and 3-dimensional bodies, then we would also have a y-coordinate for that center of gravity and a z-coordinate for that center of gravity. Now, notice that the center of gravity G is merely a point. It is a point with coordinates x bar, y bar, and z bar. We can define the center of mass, also known as C sub m, in terms of the center of gravity if we take the gravitational acceleration to be a constant. In other words, if we assume that our body is experiencing force from a constant gravitational field, which is the case for most of the examples in this class, then we can define the weight of an infinitesimally small section dW as the product of the gravitational constant times the differential mass of that section. We can also define the total weight of our bar as the product of mass times gravitational acceleration. And you should be familiar with this equation from physics. Now, if we take these definitions and we substitute them into the coordinate for the x location of the center of gravity, then you'll see that we will have a gravitational acceleration term in the numerator, which we're treating as a constant. Because we're treating this term as a constant, we can move it out of the integral, and then it will cancel out with the gravitational acceleration term in the denominator, giving us the x coordinate for the center of mass. We can repeat this process for the y coordinate and for the z coordinate, and that is how we find the coordinates for the center of mass. Now, when you start solving some of your problems, you'll see that the center of gravity and center of mass will have the same value. However, this does not mean that they will always be the same. The center of mass is the same as the center of gravity only when the gravitational acceleration is taken to be a constant. In this class, this will most likely be the case, but in future classes, this may not be so. Finally, we can define the centroid, which we express with the variable c, in terms of the center of mass if we assume that our body is homogeneous. What I mean when I say that our body is homogeneous is that we can take the density to be a constant term. If our density is a constant term, then the differential mass of that infinitesimally small element dm should be equal to the product of the density of that section times the volume of that section dv. Similarly, the mass of the total mass of the rod should be equal to the product of the density of the rod times its volume. Applying these relationships into our coordinates for the x location of the center of mass should leave us with a density term in the numerator, which we can take out of the integral because it is a constant, and cancel it with the density term in the denominator, giving us an x coordinate for the centroid. We can repeat this process for the y coordinate and for the z coordinate, and this will give us the location of the centroid. Now, again, it may seem like the centroid and the center of mass are the same thing. However, notice that the centroid only depends on the geometry of your body, not on the density or mass distribution of that body. If our body is three-dimensional, we will most likely have three coordinates for our centroid, and we will integrate over a volume. If our body is two-dimensional, we will most likely have two coordinates for our centroid, and we will integrate over an area. If our body is one-dimensional, we will also have maybe two coordinates, and we will integrate over the length of that body. But we're going to talk more about this in a future lesson. Now, if our bodies are simple, then finding the center of gravity, the center of mass, and the centroid should be an easy thing to do. However, if our bodies have more complex shapes, then we may have to split them into small sections or different sections. We call these composite bodies, where we take a body with a complex shape and split it into small sections that have easier to manage shapes, such as triangles and rectangles. For composite bodies, the total weight is found by adding the weights of the individual sections. And the center of gravity, the center of mass, and the centroid are found by taking a weighted sum of the centers and centroids of those individual sections. Now, this is actually the same process we followed in order to find the location of the resultant force of a composite distributed load.